You know, we use electricity every single second of the day, but have you ever stopped to think about what it's really doing? It's more than just turning on a light. Electric current has these incredible, invisible powers that, honestly, shape our entire world. So let's pull back the curtain and take a look at the forces hiding in plain sight. All right, let's kick things off with a little puzzle. Imagine a simple copper wire, just like you'd find anywhere. Do you think you could suddenly act like a magnet? I mean, it sounds kind of impossible, right? Almost like something out of a comic book. But is it?
Well, here's the proof right here. What we've got is a super simple circuit, nothing fancy, just a battery and a wire. Now I want you to watch what happens when we put a compass next to it and turn on the power. See that? The needle just jumped. The only thing that can move a compass needle is a magnetic field. So that ordinary wire, just because it's now carrying a current, has become a magnet. How cool is that?
That little twitch of the compass needle reveals something absolutely huge. A deep, invisible connection between two of nature's most basic forces, electricity and magnetism. Let's dive a little deeper into this. This phenomenon has a name, of course. It's called the magnetic effect of electric current. And it's a fundamental rule of our universe. Anytime an electric current flows through a wire, or any conductor, it creates a magnetic field around it. But here's the really neat part. The second you stop the current, poof, the magnetic field is gone. It's basically an on-demand magnetic force. Now, people didn't always notice. For the longest time, electricity and magnetism were seen as totally separate things. The person who first figured this out was this scientist, Hans Christian Ørsted. Way back in 1820, he was giving a lecture, and he just happened to notice that a compass on his table was twitching every single time he turned an electric circuit on and off. That one little observation completely changed science forever. Okay, so knowing that electricity can create magnetism, well, that opens up some really exciting ideas, doesn't it? What if we could control this effect? What if we could build our own magnets that we can turn on and off whenever we want? So that leads us to a really practical question. Can we actually use this effect to build a magnet from scratch? And the answer is not just yes, it's that it's surprisingly easy to do. And when I say simple, I mean it. All you need is a regular iron nail, some insulated wire, and a battery. You just wrap the wire tightly around the nail, creating a coil, and then you connect the two ends of the wire to the battery. That's literally all there is to it. And just look at the result. Before you connect the battery, it's just a nail with some wire on it. But the instant you connect that battery, it becomes a powerful magnet, easily picking up all these paper clips. We just took an invisible force and made it do real work. So what we've just built is called an electromagnet. It's basically a temporary magnet. It only works when electricity is flowing through that coil of wire. And that iron nail we put in the middle, that's called an iron core, and its job is to concentrate the magnetic field and make it much, much stronger. Now, this isn't just a fun little desk experiment. This exact same idea is used on a massive scale. Think about scrapyards. Those giant cranes use enormous electromagnets to lift entire cars. The operator just flips a switch, the current flows, and the magnet turns on. They pick up tons of metal, move it, and then flip the switch off to drop it. It's incredibly powerful and precise. But you know what? Magnetism isn't the only trick electricity has up its sleeve. If you've ever actually made one of those electromagnets, you might have noticed the wires start to get a little warm. Well, that warmth isn't a mistake. It's another one of electricity's hidden powers. To see this really clearly, we can set up another simple circuit. This time, we're using a special kind of wire called nichrome wire. When we connect it to a battery and complete the circuit, well, let's just say it gets hot. Very, very hot. You definitely wouldn't want to touch it. This is known as the heating effect of electric current. As electricity, which is just a flow of electrons, moves through a wire, it bumps into stuff. It faces opposition. Scientists call this resistance. And all that bumping around, that friction, converts some of that electrical energy directly into heat energy. Some materials, like this nichrome wire, have really high resistance, which means they get super hot. And once you know about this heating effect, you'll start seeing it absolutely everywhere. It's the exact principle that powers the electric kettle for your tea, the room heater that keeps you warm, the hairdryer, the electric iron. All of these things are just cleverly designed to use electrical resistance to generate heat. The secret inside all of them is something called a heating element. It's just a special coil of high-resistance wire.
By pushing a lot of current through it, we can efficiently turn electricity into useful, controllable heat, whether it's for ironing a shirt or just warming up a room.
So, we've seen electricity make magnetism, and we've seen it make heat. But where is the electricity in these simple circuits even coming from in the first place? Let's take a closer look inside the power source itself, the battery.
You know, the very first type of battery was called a voltaic cell, and the idea behind it is just brilliant. You take two different kinds of metal, these are called electrodes, and you stick them in a special conductive liquid called an electrolyte. A chemical reaction starts up between the metals and the liquid, and that reaction actually kicks electrons loose, creating a flow of electric current. It's chemistry making electricity.
And believe it or not, you can prove this works with stuff from your kitchen. Look at this. This is a battery made out of lemons. The acidic lemon juice is the electrolyte, and the pieces of copper and the iron nails are the two different metals. You string a few of them together, and you can actually get enough power to light up a small LED. And wow, has battery technology come a long way since then. It all started back in the 1700s with these messy, wet voltaic cells. That eventually led to the compact, dry cells that we use in remote controls and toys. And now, we're living in the age of powerful, rechargeable batteries that are literally changing the world. I mean, think about it. Our entire modern life runs on these advanced batteries. We've got the single-use dry cells for small things, but then we have the powerful, rechargeable lithium-ion batteries that are the heart of our phones, our laptops, and even our electric cars. So there you have it. From one simple, invisible flow of electric current, we get two incredibly powerful effects that have built the modern world: the power to create magnets on command and the power to generate controlled heat. Pretty amazing. Which, of course, leaves us with one last really fascinating question. We've proven pretty easily that an electric current can create a magnetic field. But does that connection work both ways? Could you use a magnet to create an electric current? Now that's a question for another day. Thanks for joining me.